In this third and final part of the presentation, we'll see how to handle nonlinear loads, specifically that of a parabolic load, before looking at general power series loads. Then we'll derive the global slope, moment and shear equations before looking at load vector V in more detail. Lastly, we'll just follow the equations and speculate on some of the results. When dealing with nonlinear loads, we can't use the formulae for UN or Vn or the general expression for UAX, as they all contain alpha and beta, which are valid only for linear loads. Instead, we have to go back to the original definitions of load vectors U and V for multipoint loads, which are the sums from 1 to R or S of Fm times vector Am, and treat the solid load as if it were a multipoint load by replacing any occurrences of X with Am. The multipoint deflection equation is obtained, then converted back into a solid load deflection equation by replacing any multipoint quantities with solid load ones. As an example, consider a simply supported beam having a solid parabolic load over its whole length L. Let it have the standard parabolic load distribution. F of x is equal to 4f0 into x over L minus x squared over L squared, which can be rewritten as 4f0 over L squared into Lx minus x squared, where f0 is the magnitude of the load at the midpoint of the beam. To turn this into the equivalent multipoint load, we replace x by Am to get the multipoint load equation Fm is equal to 4f0 over L squared into Lam minus Am squared. Once we have Fm, we can determine the load vectors U and V. Looking at load vector U and substituting for Fm from the previous slide, we can easily pick out the components of U. For example, U1 has L times 1 power of Am minus 2 powers of Am, so this is easily generalized to Un is equal to the sum of 4f0 over L squared into Lam to the power n minus Am to the power n plus 1. And using the results of the Am summations from an earlier slide, we can carry out these summations to give Un is equal to 4f0 over L squared into Lrn plus 1 minus Rn plus 2. At this point, we're still dealing with a multipoint load, so we need to convert the multipoint Un into solid load Un, which we do as before by letting B go to naught. We know from earlier that as B goes to naught, Rn goes to R bracket n over n, which is equal to curly brackets n, which is defined to be x to the power n minus a to the power n all over n, which reduces to just x to the power n over n here, as the load covers the whole beam, so a is equal to naught. Substituting for Rn in Un gives this new formula for Un, which can be written better in this form. We can determine the Un from here, with U1 being equal to 4f0 x squared times 3L minus 2x all over 6, and U2 being 4f0 x cubed times 5L minus 3x, etc. Going through the same process for load vector V and components Vn, we find that the Vn are given by this equation, from which we get V1 is equal to 4f0L over 6, and V2 is equal to 4f0L squared over 12, etc. Knowing Un and Vn, we can now evaluate the vector matrix products in the global deflection equation, which for a simply supported beam is 6ei y of x is equal to uax plus 1 over L into v dtx, as j over Lp is equal to 1 over L, as J is equal to P is equal to 1 for a simply supported beam. Writing out the expansion of the vector matrix product uax, which is valid for all load types, and v dtx for a simply supported beam, we get this form for the global deflection equation in terms of F0. To write it in terms of the load weight W, we know that W is equal to the integral from 0 to L of fx dx, which evaluates to 2/3 F0L, and substituting for F0 gives us the final form for the deflection due to a parabolic load on a simply supported beam. Again, this is exactly the same result as would be obtained using standard methods. So far, we've used two different methods for determining the load vectors u and v and their components un and vn. One method for linear loads involving alpha and beta, and a different one for nonlinear loads. It would be nice if we could use just one method for both types of loads. We can do this if we write the continuous load distribution f of x as a power series, such as f of x equals the sum from k equals 0 to p of ck x to the power k, where p would be equal to 0 for a uniform load, equal to 1 for a linear load, and greater than 1 for a nonlinear load. The coefficients ck depend on the load profile. The multipoint version of this would be fm is equal to the sum from k equals 0 to p of ck am to the power k, and load vector u would be given by u is equal to the sum from m equals 1 to r of fm am, which becomes, on substituting for fm from above, equal to the sum from m equals 1 to r, the sum from k equals 0 to p of ck am to the power k, times the vector 1 am squared am cubed. The components can be seen to be equal to un is equal to the sum from m equals 1 to r, sum from k equals 0 to p of ck am to the power k plus n minus 1. If we reverse the order of summation and carry out the sum over m, we're left with the sum over k of ck r k plus n, which, after using the definition of rk plus n, becomes un equals the sum from k equals 0 to p of ck curly brackets k plus n. Vn is found to be almost the same, but with square bracket k plus n instead of curly bracket k plus n. The definitions of curly bracket n and square bracket n are reproduced here. For a cantilever beam, the global deflection equation is 6ei y of x is equal to uax plus v dtx, where the uax expansion gives minus x cubed u1 plus 3x squared u2 minus 3x u3 plus u4, and v dtx gives x cubed v1 minus 3x squared v2. When we substitute for the un and vn, we get this lengthy equation. The cantilever beam is the simplest of beams, but we can see that the resulting global deflection equation is quite long and complicated, and we haven't even carried out the summations yet. As such, this goes against the original goal of developing simpler deflection equations, so I don't think this power series approach offers any benefits in that regard. Better to use either the linear load method or the nonlinear load one on a case-by-case basis. This power series approach might be more useful for computer-generated deflection curves, as generality is more important there than brevity. In this slide we look at global slope, moment, shear and load equations. The load equation is only non-zero underneath the load, so can't really be called global, but I've included it here for completeness. The slope equation is obtained from the deflection equation by differentiating with respect to x, indicated by the dash. When we differentiate the global deflection equation, which contains two terms, we get a four-term global slope equation. But some of these terms turn out to be zero. For example, we know that load vector v is constant, so v dash is identically zero, and the v dash term disappears. If we look at the u dash term region by region, we know that load vector u is zero to the left of a load, so u dash will be zero, as will u dash ax. To the right of a load, we know that load vector u is equal to load vector v, which is constant, so u dash is equal to v dash to the right of a load, which we've just seen is zero, and so u dash ax is zero to the right of a load also. Underneath the load, u has components un, given by alpha curly bracket x minus beta curly bracket x plus 1. Using the definition of the curly brackets, this is equal to alpha x to the power n minus a to the power n, all divided by n, minus beta x to the power n plus 1 minus a to the power n plus 1, all divided by n plus 1. Then if we differentiate this, we get un dash is equal to alpha x to the power n minus 1 minus beta x to the power n. This can be written as x to the power n minus 1 times alpha minus beta x. Now the vector matrix product u dash ax is just a copy of the uax product with un dash instead of un. So we have that u dash ax is equal to minus u1 dash x cubed plus 3u2 dash x squared minus 3u3 dash x plus u4 dash. Substituting for the un dash, we get that this is equal to alpha minus beta x into minus x cubed plus 3x cubed minus 3x cubed plus x cubed, all of which cancels each other out to give u dash ax is equal to 0 underneath the load. So u dash ax is 0 across the whole beam, and we can eliminate that term from the global slope equation also, leaving just two terms, u ax dash and plus j over lp v dt x dash, where x dash is the vector 0, 1, 2x, 3x squared. We can differentiate this global slope equation to get the global moment equation, and so on, where we'll need x double dash, x triple dash, shown here, and x quadruple dash, which is identically 0. The results of the differentiations are shown here, with the global moment equation, the global shear equation, and the global load equation. We can see from this last equation that for a uniform load, where beta equals 0 and alpha equals w, the load per unit length, that EI quadruple dash x is equal to minus w, which is the standard result. What we've covered up to now is really all there is to the theory behind the global deflection equation and its derivatives. In the remaining slides, I'll look at some of the symmetries and properties of the beams that this matrix formulation of the global deflection equation throws up, and speculate on some of the results. Here I'm going to look at load vector v, in particular its components vn, and see if any of them correspond to physical quantities. So first of all we'll look at v1, which is the sum from 1 to s of the point loads fm. This just gives the total load on the beam, so v1 is equal to w, the total weight of the load, and we've seen this result before. v2 is the sum of fm am, where each term is the moment of that particular point load about the origin, which is at the left-hand edge of the beam. v2 is therefore the moment of the load about the origin given by w times xcm, where xcm is the distance of the centre of mass of the load from the origin. v3 is the sum of fm am squared. Here each term looks like a moment of inertia, but I don't think the sum of these can be translated into a total moment of inertia, as this would require an axis of rotation which isn't obvious, so I'm not sure if v3 has any physical meaning. v4 is the sum of fm am cubed. I'm not sure what quantity dimensions of weight times length cubed corresponds to, so I'll say that v4 has no physical meaning either. But knowing the physical meaning just of v1 and v2 can make evaluating the deflection equation easier. This is particularly true for the deflection to the left of a load on a cantilever beam, where only v1 and v2 are involved. v1 is always equal to the weight of the load, and v2 is the moment of the load about the origin. If we have a rising triangular load, as shown here, the centre of mass lies at a point 2/3 of the way along from the left-hand point of the triangle, or 2d over 3, where d is the extent of the load. So the centre of mass distance is equal to a plus 2d over 3, and so v2 is equal to w into a plus 2d over 3. Substituting these values into the deflection equation, we get the standard result for the deflection to the left of a rising triangular load, that 6ei y of x is equal to minus w x squared into 3a plus 2d minus x. Now we're going to look at a duality in the deflection equations either side of a point load. Using earlier notation, if x lay to the left of a point load, that part of the beam had a deflection equation y_L of x, and if x lay to the right of a point load, that part of the beam had a deflection equation y_R of x. So if we want to know the deflection to the left of the load, we'd use y_L of x and use y_R of x to the right of the load. But because of the duality in these two equations, we can in fact use y_L or y_R on either side of a point load. To see how this works, we start with a matrix relationship between the bending matrices D and dt, which we derived towards the beginning of the presentation, namely that d minus dt is equal to LP over J times A, where A is a constant matrix equal to d minus dt for a cantilever beam. Then we can write y_L of x, which is equal to kFA dtx, as kFA into d minus LP over J times A x, where I've substituted for dt. Expanding this, I get two terms, kFA dx and kF LP over J AX. The first term is just y_R of x, and the second term can be rewritten using the definition of k as FAAX all over 6EI. The vector matrix product in the last term, AAX, multiplies out to give minus x cubed plus 3x squared a minus 3xa squared plus a cubed, which is just equal to minus x minus a all cubed. So we end up with a relationship between y_L of x and y_R of x, namely y_L of x is equal to y_R of x plus f into x minus a cubed, all divided by 6EI. If we call the difference between y_L of x and y_R of x delta y of x, then delta y of x is equal to f into x minus a cubed over 6EI. Delta y of x is beam independent. This means that the difference between the deflection equations either side of a point load, f into x minus a cubed over 6EI, is the same for all beam types. We can use this duality between y_L of x and y_R of x to our advantage when calculating the deflection due to a single point load. For example, if we want to know the deflection at a point H to the left of a point load on a cantilever beam, we would normally use y_L of x to calculate it. y_L of x for a cantilever beam is given by the nonlinear equation minus fx squared into 3a minus x all over 6EI, which is to be evaluated at x equals a minus h. I've shown you the few of the steps in the calculation, and the result is that y_L of x is equal to minus f times a squared into 2a minus 3h plus h cubed all over 6EI. This calculation is fairly lengthy as the equation is nonlinear in x. Alternatively, instead of using y_L of x, we can use the dual equation y_R of x plus delta y of x, which is equal to minus fa squared into 3x minus a all over 6EI plus f into x minus a cubed over 6EI, all evaluated at x equal a minus h. The first term is easy to evaluate as it's linear in x, and the second term, the difference term, is even easier, the bracket being just equal to minus h cubed. The result is the same as we obtained by using y_L of x, but is a lot easier to calculate. So now we have a choice between using y_L of x or y_R of x or their duals, and we can choose whichever is the easier to use. We know that by differentiating the deflection equation repeatedly, we can get the slope, moment, and shear equations. The same is true for the dual equations. By differentiating the dual deflection equation, we can get dual slope, moment, and shear equations. This is done most easily by differentiating the difference, delta y of x, to create differences in slope, moment, and shear. So the difference in slope, which I've called delta theta of x, defined to be theta L of x minus theta R of x, is found from delta y dash of x and is equal to f x minus a squared over 2ei. The difference in moment, delta m of x, defined to be m L of x minus m R of x, is found from delta y double dash and is equal to f x minus a over ei. Lastly, the difference in shear, delta v of x, defined to be v L of x minus v R of x and given by delta y triple dash, is equal to f over ei. So if, for example, we want to calculate the moment at a point to the left of the load, we can use either mL of x, the equation for the moment to the left of the load, which is what we would normally use, or we can use mR of x, the equation for the moment to the right of the load, plus f x minus a over ei. We can choose whichever seems to be the easier option. Similarly, for a point to the right of the load, we can use either mR of x or mL of x minus f x minus a over ei. Having looked at the differences across a point load, we'll now look at the differences across the boundaries of a partial solid load. Consider the generic beam and load shown below. We know that underneath a solid load, the full deflection equation applies. We also know that to the left of a partial solid load, load vector u is 0, so the product uax is 0, and the deflection in that region is given by 6ei y of x is equal to j over L to the power p v dtx. To the right of a partial load, we also know that load vector u is equal to load vector v, so in that region the deflection is given by 6ei y of x is equal to vax plus j over Lp v dtx. Looking at these three regional deflection equations, it's immediately obvious that the same term, j over Lp v dtx, occurs in all three regions of the beam. This suggests that the dominant factor in determining how a beam bends is how it bends to the left of the load. The other two regions just add their own contribution, uax underneath the load and vax to the right of the load. Because the deflection in each region has a common term, if we look at the difference across a load boundary, this term will disappear. If we use the subscripts L, U and R to refer to the regions to the left, underneath and to the right of the load, then the difference across the left-hand boundary of the load, from underneath the load to the left of the load, will be delta UL, which will be the negative of delta LU, taken in the opposite direction. Similarly, the difference across the right-hand boundary, from right to underneath, is delta RU, and the difference across the whole load, from right to left, is delta RL. So, for example, the difference in the slope equations across the entire load will be given by 6ei delta theta RL is equal to vax dash. All these cross-boundary differences depend on matrix A, which is a constant, so these differences are beam independent. This means that the differences in the formulae for deflection, slope, moment and shear across a given boundary will be the same for all four beams for a given load. This result isn't immediately obvious when looking at these equations written in their usual form, but it is using this global matrix formulation. In previous slides, we've met the load vectors u and v, which occur in the global deflection equation reproduced here. This has two terms. The first, uax, is beam independent, as matrix A is a constant. The second term, j over Lp v dtx, is beam dependent. So if we multiply out v dtx for each beam, we get the following results. The first term, v1x cubed, is the same for all four beams. So we can take this out of the v dtx and write the global deflection equation as 6ei y of x is equal to uax plus j over Lp v1x cubed plus j over Lp v hat dtx, where v hat is just load vector v without component v1. So we'll call this a reduced load vector. If we look at the first two terms in the expansion, we see that these are the same for all beams apart from the simply supported beam. So we can write the global deflection equation for these three beams as 6EI y of x is equal to UAX plus J over LP into V1x cubed minus 3V2x squared plus J over LP V tilde dtx, where V tilde is load vector V without components V1 and V2. To distinguish between these two reduced load vectors, we can call V hat a simply reduced load vector, as it's missing just one term from load vector V, and V tilde a doubly reduced load vector, as it's missing two. Looking at this last equation, we see that the first two terms on the right hand side are just the two terms of the cantilever beam, so we can rewrite this equation as y PCFE of x is equal to y cantilever of x plus j over 6EILP V tilde dt PCFE x, where the subscripts PC and FE refer to propped cantilever and fixed end beams respectively. We now have a relationship linking these three beams. It looks like the cantilever beam acts as a kind of underlying beam for the propped cantilever beam and fixed end beam, onto which they each add their own unique contribution via j over 6EI LP V tilde dtx. By differentiating this relationship, we can derive the corresponding relationship for the slope, moment and shear equations between these three beams. Why is a simply supported beam the odd one out here? Maybe it's because the other three are fixed at the left-hand edge of the beam and so have zero slope there, whilst the simply supported beam isn't fixed and so has non-zero slope. This is the end of this presentation on a global deflection equation. I hope you found it interesting and maybe also useful. Full notes can be found on my website at www.gammamunew.co.uk with additional worked examples. During the course of this work, back in 1985, I thought I would need to use Bernoulli numbers to generalize the summations, so I did some work on those also. I didn't use them in the end, but I've included these notes on my website also. From time to time I'll add other material to the website, either factual or speculative, on various topics, so please check every now and then. That's all. Thank you for your time and goodbye.